Everyone, in this video I'd like to introduce a little bit about this Laplace transform. I think it's right motivation to look at the first order linear equation, which is y prime minus s y equals phi, where s is a constant, s a constant, and phi is a function of x. And we know how to solve this simple differential first order equation. Even this s is a constant here, so I think it's one of the simplest example. So, and I hope this comes to your mind. It's called integrating factor. So it's called integrating factor. That integrating factor is e to the negative sx. So what that means is if you multiply these e to the negative sx to the both side, especially the left hand side where this y prime and y are, that becomes a derivative of single term, but the product of two factors. So let me write it like this. After you multiply e to the negative sx, y prime is there, and s times e to the negative sx, and y is there, and we do the same thing, e to the negative sx, and phi x there. Now from here, magic happens. The left-hand side in here becomes the derivative of this time e to the negative sx and y. So y is kind of isolated here. The two term appearing in here and there becomes a one term, and from here we can do antiderivative, one single operator we have to solve this relatively complicated differential equation. So we call it out, and Vx. So I have already introduced this operational term, so we'd like to look at this as an operation to unfold to get to y. Next thing we do is integrating from 0 to x and switching everything to dt and e to the negative st, and here is a function in terms of t, so it and dt. And we do the same thing to e to 0 to x and e to the negative st. Now this becomes phi t dt. This, since we don't know much about this phi t, that's going to be the expression we use, but because the derivative and integration, the left-hand side has a different expression, using a fundamental theorem of calculus, that's an antiderivative of the integrand inside. So here's e to the negative st, yt evaluated at 0 and x, and that's the that equals, let me write it this way, right hand side. So let me summarize it over here. So what happened if you evaluate left hand side, you have negative e to the sx, yx, and minus, when I plug in x equals 0 there, and we have 0. I forgot to explain this choice of this value 0 here. In Laplace transform, the context of a Laplace transform is we're dealing with, most of the time, the function for which this is defined in all real numbers, or at least defined around 0. This initial position, it is not of such importance, so you can either shift it around and things like that. As most of the example we look at it here with this Laplace transform is a function that are defined in all real numbers. In particular, if you look at the initial value problem at 0, that's going to be extended to all negative infinity to positive infinity. But if that's too much restriction to you, then we're going to just focus on the solutions around 0. And that's why it's choice in here. And especially for this integrating factor, if you plug in s equals 0 there, that simplifies this factor that appears here a lot. So that's another the reason we're choosing this one. So that's one choice we make about this Laplace transform, but I don't think, what I'm trying to say here is I don't think we lose a whole lot of generality out of making this choice in here. So because of that choice in here, when you evaluate this one, e to the negative s times 0, that's simply y equals 0, that's where I use that. All right, then right hand side is whatever that is. Okay, so right hand side, I'm going to keep it that way. So the focus is on the left hand side. what is it that we do to the left-hand side, and then it became like this, where this is just a value. If it is not unknown, if you're just looking to doing something to the function that are given in that form, and that changed to this form, and that's good. It's just the value of the function, and the derivative disappeared. Only the solid the y part appeared there with known function multiplied. So this operation is of interest in here, not this the right hand side right now. So we're going to describe that operation in operational term. So let me describe it this way. There is this y prime and constant s times y. And to that function, if I use this operational symbol, it could be the following. We multiply this e to the negative sx. That's one type of operator. Given function, we multiply this non-zero, never zero function there, and then we integrate from 0 to x. So this is not really the usual integral. This is an operational symbol. So I'm going to call this one as an one operation, broken into two pieces. First, multiply this exponential function, and then integrate from 0 to x. So I'm going to call this operator is curly L with a subscript s, because that's some s that we're playing with there. And this is not yet Laplace transform, so I'm going to use this twig tilde in here. So I'm going to call that operator this tilde. So let me write it this way. This L tilde operator with this some s involved in there. S is some parameter, y prime. So over a negative s times y is equal to e to the negative sx y minus y of 0. That's the summary of all this discussion. So let me box that. So we just defined an operator called ls tilde, such that if you hit this ls tilde with this very special form of this first order expression that involves first order derivative, then it unfolds nicely. Y is mainly just a summary of different way of writing this product rule. But there is this magic factor, e to the sx is involved, so plus some this integrating factor phenomenon. So together we write, summarize all this phenomena into operational language like this. So those were just the motivation, and I didn't even specify clearly what these operators are. So let me go ahead and define the first definition. This is not Laplace transform. This is preliminary part of Laplace transform. We're going to define this operator with this parameter s involved. If I give you a function y, what we do is we're hitting this operator. So first we multiply the function y by e to the s times x, but we're going to eventually hit the integral, so you have to change to dummy variable yt there. So that's first part of this operator, and then we integrate from 0 to x and dt in here. So this is called this ls tilde operator. Once you have that defined, then we just saw that the property that this one satisfies is that, so let me rewrite it like this. So from early observation, we know that is ls tilde y prime minus, sy is equal to that function, e to the negative sx, y minus y0. So this is actual function. This is not an equation. We have a function, and we happen to have this special expression of that function written in here. And if you hit it with this operator, it becomes this simple like this. So I want to remember x is a variable, s here is a relatively constant. So I'm going to write down here s is a constant, and using the linearity, if you look at it here, and you may believe that this is a linear operator and multiplying, you can also, of course, you can check. So because of the linearity, so something really nice happens in here. So this L tilde operator, because of the linearity, it splits like this, and this will be applied and distributed over to that side, but s is the constant multiple, and linearity pull this one out, and you have an L tilde operator there, and e to the negative sx, y minus y of 0. And because of the linearity and s being a constant, it realized that it has very nice effect if you solve this thing for this operator on y prime. Then if you move this thing to over here, then he organized it like this: ls tilde y and minus y0 and this functional part e to the negative sx y. So what this one did is that there's this operator with s is kind of parameter involved in there. What it does is that if you hit it with that operator, what happened to that is a y prime, whenever you have derivative in there, it can be rewritten as original function. There's no y prime in there. With this s as a parameter outside, the value of the function and the function value in here. So it is not easy to see what is the advantage of doing these things like that, but I guess Laplace noticed that changing this y prime to an algebraic polynomial, more specifically as a polynomial expression in S, is something that is very interesting. It's because of the following. So I'm putting the huge star here. The most important fundamental theorem of this differential equation course is existence and uniqueness. Think about this structure in here. We have y prime because of the linearity and is transformed into that shape. This has polynomial in S part and plus there's some functional part. But this, he realized this polynomial part really captures the coefficient phenomenon of whatever the first order equation you have it there, and it involves initial value y0. And if we're dealing with solution of differential equation dE here, then this amount of information is sufficient to capture or describe or associate with the solution because of existence and uniqueness. If you have some initial condition involved in this polynomial part, and the structure of this polynomial exactly kind of captures the shape of the equation there, then this much of the information is sufficient information to capture the nature of the solution of the differential equation they're dealing with. So this part is this is an important observation. The structure of a differential equation is turned into a polynomial algebra in S, and it had some initial value built into it. And to him, that was a sufficient information to capture every solution in this whatever the differential equation we're looking at. So this functional part, although it's appearing here, is probably not important to carry this around. This polynomial algebra S and with this part in it, and with this initial value involved, is again sufficient to deal with all the solutions of the differential equation. So that's a motivation. So he's going to do one more operation to this whole thing so that this one disappears. Now here's a trick. What operation are you going to apply to here to get rid of that? And this operation eventually take this y prime to this only polynomial algebra in S, and that will be a fantastic thing. So the key thing is that S is a constant, and when we look at this as a polynomial algebra, it's all about S in there. So X is not important to look at this as a polynomial structure. So what should we do to X to get rid of this one? One idea he came up with, send, maybe that's a good term, X to infinity. If S is a positive, and you notice that this e to the negative sx as x approaches infinity is huge decaying factor. If y of x is not fast growing function, normally like it's sine x and a polynomial and those functions, and this will definitely kill this one to the 0. So if S is a positive, and then we may hope there's a good chance for in many of the ordinary functions, we may hope that e to the negative sx, while this s is fixed and x is approaching infinity, then yx approaches 0 as x approaches infinity. So for example is y being a polynomial, or usual trig function, and these are the typical example. So think about this, s has to be some positive number to have these conditions, and when you think about exponential case, exponential functions, that still works for some cases. But if it is exponential function, you can imagine the exponential function that grows a lot faster than constant times e to the x there, and e to the negative constant times that x. In that case, it's not going to converge. So as x approaches infinity, remember that has operator that is 0 to x and e to the negative sx. So this changes to t when you actually integrate. Well, let me change to t and x there, and there's a function there in dt. So x going to infinity is usually we use this typical improper integral notation. We simply change that x to infinity. So at this stage, there's the question of whether this improper integral will exist or not, but we're only going to consider this standard basic elementary functions. And if not, when you state some theoretical statement, we always assume we're dealing with a function, all this improper integral when x is going to infinity, they exist. So let me write that down. Then 0 to x to e to the negative st, yt dt, that is now denoted as this operator done on y like this. Then as x approaches infinity, then we can write it like this in the next line. And this improper integral notation, e to the negative st, yt dt, is really that x approaches infinity. This is a function on x, right? So we're looking at this as a function of x. Once you send this one into infinity, this is no longer a function of x. This is just a value. Say, I'm going to write it down like this. Is a value, not a function. To specify the variable and not a function of x anymore. We send x to an infinity. But this value still has this unknown constant involved in here. So we should say the value, not a function of x, depending on this unknown choice of a constant parameter s. So since s is undetermined, we can look at this as a function of s again. So, but we shouldn't just call this one as a function going to the function. This function going to the value that depends on additional parameter. So I guess that's why one of the reasons they didn't call this one an operator, but called a transform as something transform this entire phenomenon with some other parameter involved in here. This captures not the behavior of the function itself, but the behavior of this differential behavior. I think that's the right way to say that. This transform captures this differential behavior rather than the functional behavior itself. So finally, our definition of Laplace transform. Now we lose this tilde by sending x to infinity, so we define this Laplace transform of function y. No one except me use the following notation, but I think it's good to have that s in there and emphasize it, what it plays, the role it plays in the previous stage in there. So rest of the world and all other mathematicians will use Laplace transform without that s in it, but I like that s in it. It just helps us to remember what kind of transform we went through under this one. But the simple definition is that this one is defined as a value of integral of this integral, improper integral, where s is unknown parameter involved in there. So that's the definition. All is different is x changed to infinity, and that's that. And it kind of inherits a lot of good properties that we've I didn't show a lot of property, but this important property we went through in here. Let me write that down. So let me remind you of what we had before with the tilde operator. And if you do y prime, what we have is this s pops out, and this tilde operator, and minus the initial value, and plus this real function term e to the sx and times yx. And if we assume this approaches 0, we're looking at that type of a function, and assuming this one exists, and if this improper integral exists, this must approach 0, so there's no choice, that must approach 0 as x approaches infinity. That is something you might have learned in Calculus 2. Improper integral to the infinity exists, that tail term must approach 0. So that's, if not, it's not going to exist. So, but there's several different ways to verify this. But this is one of the technique that he came up with. And if you send x to the infinity, this will disappear. And finally, what this captures, so we can remove as x approaches infinity, this becomes the typical Laplace transform. The derivative, now it becomes polynomial algebra of Laplace transform on the original function minus y0, period. So that's the nice property that translates linearly the one derivative to this no derivative through this polynomial algebra. You can apply this algebra and over to the second derivative, to the first derivative, and first derivative to the 0th derivative. So all this linear differential operator can be turned into a polynomial algebra in S, and that's why it works, and that's the main accomplishment. So let me write that down. Linear differential algebra became polynomial algebra in S. So solving differential equation becomes dealing with this algebra of a polynomial in S. Okay, so rest of the things that you learn in a standard differential equation course is about transform this one and do some polynomial algebra in S.